Howdy everyone and welcome back. Today we're going to talk about electric fields. And it may feel like a weird concept because we just talked about electric forces, but it turns out they're pretty interrelated and it's more of a different way of looking at the same thing. So the basics are electric fields are emitted by electric charges. So these go outward from positive charges and they go inward for negative charges. And more lines together means that it's a stronger electric field. So why are we learning this? Well, it's another way of looking at the same thing as when we were looking at with electric forces. It's like watching a movie, but they switch the character's perspective. It's another way of doing the same sort of problems and looking at the same thing. And a lot later in the class, we'll actually be using electric fields instead of electric forces. So there's two interpretations of electric charges affecting each other. One is what we've learned before. Electric charges just straight exert forces on each other. And that's what people have been looking at for a long time. That was Newton's view on how gravity worked. But there's another interpretation that developed a little bit later, and it's what we're going to be talking about today. And it turns out has a little more basis in reality. And that's that electric charges actually just create electric fields. And it's the electric fields that exert forces on the other charges, not directly the charges on each other. So there's two reasons why we might want to be interested in this new interpretation of electric fields. And one is pragmatic and how we do problems, and the other one is actually based on reality and things that we've seen in experiments. So the first reason, the pragmatic reason when we're doing problems is why we care about electric fields, is that if we know the electric fields, we can find the force on any charge we want. Maybe we do the same problem, we put a different charge, a second charge, in the influence of this electric field. We don't have to recalculate the whole problem and start from scratch. We have actually almost the whole thing done. We can put in whatever charge we want. And the relation between electric fields and electric forces is just multiplying that second charge. So electric fields are just created by a single charge. So if we wanted to find the force from something else, we just bring in that second charge, multiply it. That's telling us that the electrical force is only going to be in the same or opposite direction as the electric field's pointing. And that should match up what we're thinking. We know that electric force can only be attractive or repellent. And this is what the equation is directly telling us. This is something that is generally true. So the other reason why we care about actually looking at electric fields and that exerting forces on charges instead of the charges themselves is because we've done experiments, and then we can look at a charge. We can see that there's a time delay before it's able to influence another charge over here. We know that theoretically through relativity, we've been able to measure it. It's telling us that there's actually something traveling from one charge to the other, and that's what influences. It turns out that's actually photons or light particles, but we're going to call that and quantify that, talk about it as an electric field. Okay, but how do we actually calculate the electric field? Well, the electric field created from a single charge, it looks almost identical to Coulomb's law, except now we only have one charge instead of two charges, because electric field just gets emitted by one charge. If we always wanted to find the force, we could always multiply it by the other charge in the end. And everything else here is the same. The distances between the charge and the point that we're interested, the charge of the original charge that's creating electric field in this Coulomb constant is the same. It's really almost going to be the same exact problems as we've done last time, except again, just a slightly different context. Now we're going to be calculating the electric field instead of electric force. But again, if we ever want to get back to the electric force, say we calculate the electric field from a bunch of different things all combined, all we need to do is multiply it by that second charge that's living in that electric field, and that will give us the electric force exerted on it. Okay, now it's time for everyone's favorite part. We're going to do some problems. We're going to throw some math at you. Okay, let's do it. Okay, here, so we have a electric force that's pointing downwards. It's in the green. We're told the strength of the electric force, some magnitudes, and now we know the direction because it's pointing down. And we're told the charge that we want to have sitting and living in this electric field, and we want to find the force that's exerted on it. So all we need to do, like I stated before, is that if we want to find the electric force, if we know the electric field it's living in, and we know the magnitude of the charge, then we just have to multiply these two things together. And so we do that. We notice that when we do that, we carry through that, put in our calculator, we get a negative sign, and again, a lot of these problems, we really only care about the magnitude, so we'll put in the number, but the negative sign helps us with the direction. So we get a negative sign here, that means it's in the opposite direction as the electric field. So if the electric field's pointing down, the electrical force is actually going to be pointing up in this case. Okay, so we got another big, scary problem again. This is going to be very similar to one we've done before, but let's just walk by it step by step. So this time we have three charges 2 positive, 1 negative. We have a point, here's the point we care about, and we want to calculate the electric field at this point. So all of these charges are creating electric fields. They're moving outward from the positive charges, so they're going out from this one and pointing in towards this one. And so when you make it, do a huge 2D calculation, throw it into a computer, you'll find that, it's probably some really complicated stuff out here and a point here. The overall electric field, we're only going to care about one point. We only want to calculate this one point. That's all we care about. So what we need to do is very similar to before with the Newton's second law problems, summing up a bunch of different electric forces. What we're going to do is find the electric field created by each of these charges here, and we're going to add them all up. And that's going to tell us the net electric field at that point. Again, if we wanted to find the net electric force, we can always just throw a charge in here, multiply it out in the end. Again, we can see why this approach is better, because again, if I wanted to put a different charge in the end, no problem. It's just multiplying. I don't have to do the whole problem over again. You can see where this is going to go. It's going to be similar to before. We're going to have to find the magnitudes of all these electric forces first, write out that we're going to add them all together, break that vector equation into components, and then since we have the magnitudes and a little bit of trigonometry, that should tell us all the components. Just add those numbers together. So let's first get that. Let's first get the magnitudes. So from Coulomb's law, the electric field version, all we need to know is Coulomb constant here, the charge, what's creating the electric field, say the charge of this one or this one, this one, depending on which one we're looking at, and the distance between the point we're interested and that charge. So if we're looking at the electric field created by Q1, it's going to be this distance here, and we have to figure out what that is. So fortunately, they tell us that each of these distances is 0.5 meters, and so this is halfway. This has to be 0.25 meters. And they tell us the charge of this one, okay, it's just 8 times 10 to the negative 6, or microcoulombs. Okay, we put that all in, we get that magnitude, no problem. Problem is looking at E2, looking at the electric field created by the second charge here. So this distance isn't so obvious. We're going to have to do a little bit of trigonometry. So done it here. We have this triangle here. Essentially, we draw this triangle and we transport it over here. We know that this distance is 0.5. We know that this angle is 60 degrees. Like before, we know that's halfway, and we can actually put that in our trigonometry. You can use SOHCAHTOA, 0.5 times cosine of 60. Well, that gives us half of it. Okay, that makes sense. So for this opposite side, again, we're using the sine of an angle equals the opposite over the hypotenuse, and then multiplying that hypotenuse to the other side. So that's going to tell us the opposite length. And so the hypotenuse is 0.5. Sine of 60 degrees, that tells us that this length is 0.433. That's what's going to go in our distance for E2. That is this distance here. Okay, and we know the charge there. We know that's 3 times 10 to the 6 coulombs. That will give us the electric field, the magnitude of the electric field created by that charge. So we have this one and this one. Now we need to just do E3. So the electric field created by the third charge. I think there's supposed to be a 3 there. I don't think anyone's paying attention though. Again, we know the charge, they give us that. We know the distance, they give us that. We put the magnitude of electric field, and we'll figure out all the signs in a moment. But okay, now that we have all the magnitudes, we can really write out what we want. Again, the net electric field is just going to be the 3 adding up. So what we're going to do is just like before, is we're going to write down an x and y version of these equations and then figure out what each of the components are. So after we write out each of these equations, we can ask ourselves, what is the components for each of these? Do we need to do some complex trigonometry? Well, let's look at the picture and see what's going on. So we're looking at charge 1. What direction is the electric field that it's making? Well, we know for positive charges, it always points outward. So if we look along this line of sight, it's going to be creating an electric field this direction. So when it gets here, it's going to be purely in the positive x direction. So there's no y component. We get rid of this. And this is just the magnitude with a positive sign. We just take this number that we had up here, put it in for E1. Okay, now let's look at charge 2. Electric field lines emanating outward from a positive charge. Can we look along this line of sight? It's going to be pointing down once we get to this point. The entire value for this y component is going to be the magnitude, but with a negative sign, and that's what we're going to get here. And we look at 3. Okay, it's a negative charge here, but so electric field lines point inward towards negative charges. We look at this one. Electric field that's going to be created It's going to be pointing right here. So it's also in the positive x. It looks a little weird, but this is true. So again, no y component. This is just going to be the positive magnitude. It's just going to be this number, just positive. And that's what we have down here with these numbers that we calculate up here. This one with a negative sign because we figure out the directions. Add these numbers across, including any negative signs we introduce, and that's the component of the net electric force there. Again, we can find the magnitude, use the Pythagorean theorem. We can find the angle, use the inverse tangent. That's really all we can ask from these sort of problems. But we can see, once we know that, again, I have the electric field here, put any charge I want, multiply it by this amount. I will get any electric force created by any charge I could want there. I don't have to redo the problem. That's it. That's all I have today. Thanks for joining me. It was great. Hopefully you learned something. Okay, thanks. Bye.